Okay, 7.3, the dot product between two vectors. So in this section, we will discuss multiplying two vectors. When we calculate the dot product, we do so with geometric vectors. Okay, and those are vectors that do not have a coordinate system associated with them. So the dot product between two geometric vectors, vector A and vector B, is a scalar. Okay, so when you calculate the dot product, you're going to spit out just a number. Okay, just a magnitude, just a scalar, just a number. Okay, and the dot product is defined as this right here. Vector A dot vector B equals the magnitude of vector A, which is a scalar, times the magnitude of vector B, again, which is a scalar, times cos theta. Okay, and this theta from the cos is the angle between the two vectors. Okay, so a couple things about the dot product. Observations about the dot product. The result of the dot product is always a scalar. It's called a scalar product. Okay, the dot product can be positive, 0, or negative, depending on the size of the angle between the two vectors. Okay, I want to throw this out there. Okay, two things. If we have an angle in the first quadrant, this is the A quadrant. Remember the cast rule? So cos is going to be positive. In the S quadrant, so if it's obtuse, cos is going to be negative. Okay, and then if you think about it, if you think the cos curve, and you think about when it's 0, right? Because that's, so it's positive, 0, or negative. When it's 0, this is 90 degrees, or pi by 2. Okay, so when we have cos of 90, this entire thing goes to 0. And we're going to talk about that now. Okay, so as I threw out there, the dot product is only calculated for vectors that have an angle between 0 and 180. Okay, so we're not going to worry about the T quadrant, and we're not going to worry about the C quadrant. We're only worrying about quadrant 1, the A quadrant, and quadrant 2, the S quadrant. Okay, when two non-zero vectors are perpendicular, okay, so let's talk about perpendicular. We saw here 90 degrees. That means that if vector 1 is like here and vector 2 is here, if these two vectors are perpendicular to one another, what's going to happen is they're going to have a dot product of 0. Okay, and obviously that's because cos of 90 equals 0. Right? Right in the definition of dot product. Okay, so let's talk about the sign of the dot product. So if our angle is between 0 and 90, including 0, okay, cos of theta is going to be greater than 0. Obviously, we're in the all quadrant. So vector A dot vector B is also going to be positive. Okay, remember magnitude as a recall. If we're solving for the magnitude is always positive. Okay, so we have essentially positive, positive, and then cos theta will be positive. So the dot product will also be positive. Okay, right at 90 degrees, cos theta is going to equal 0. Because cos 90 equals 0. So it doesn't matter what vector A dot vector, the magnitude of vector A times the magnitude of vector B is, because cos of 90 is going to be 0, so the dot product is going to be 0. Okay, last situation, so this is essentially quadrant 1, this is essentially quadrant 2, and this is 90 degrees. Okay. So if we're in quadrant 2, between 90 and 180, but not including 90, because 90 is like the special case here, okay, cos theta is going to be negative. So our dot product will also be negative. So The angle when the two vectors are placed tail to tail is used. Okay, so this means tail to tail. This angle, this is our theta. Okay, because this is how we define the angle between the two vectors. Okay, so example 1, two vectors, vector A and vector B, are placed tail to tail and have magnitudes of 3 and 5. So let's go vector A, magnitude of vector A is 3, and because it's respectively. So A is 3, B is 5. There's also an angle of 120 degrees between the two vectors. So this is going to be 120 degrees, and magnitude of vector B is 5. Now, the question says, calculate vector A dot vector B. So our equation is vector A dot vector B equals the magnitude of vector A times the magnitude of vector B cos theta. Okay, so filling this out, the magnitude of vector A is 3 times the magnitude of vector B is 5, and then we're going to sub in cos 120. Again, 120 degrees is used because this is how we define the angle between the two vectors. Okay, so when we put this into our calculator, we get negative 7.5. Properties of the dot product. So the commutative property holds for the dot product since all quantities in the formula are multiplied by one another. So the order of operation does not matter. Okay, so in other words, A dot B is going to yield the same result as B dot A. Okay, it's commutative. That means magnitude of A is going to be multiplied by magnitude of B is going to be multiplied by cos theta. All of these, since they're multiplied, it doesn't matter the order. So again, magnitude of A dot B is equal to B dot A. Okay, there's also something called the magnitudes property. So vector A dot vector A is actually going to yield the magnitude of A squared. So we'll show this down here. So example 2, if the magnitude of vector A equals root 7, calculate vector A dot vector A. Okay, so vector A dot vector A, another way of writing this is the magnitude of vector A squared. So in other words, root 7 squared, which is just 7. So the dot product of vector A, like A dot A, vector A dot vector A is 7. Okay, now calculate vector I dot vector I. So I'm going to just draw this in 2D. Okay, if you remember, X and Y are here. So vector I is going to be 1 unit in the X direction. Okay, so the magnitude is 1. This is a unit vector. Okay, so unit vector, and this is vector I. Okay, so we'll write B over here. So if we had vector I times vector I, what's going to happen is this is going to be, okay, magnitude of I squared. So the magnitude of vector I, which is obviously unit vector, is just 1, and then 1 squared is obviously just 1. The distributive property and the associative property with a scalar k, usually k is written like in kind of like a cursive, like lowercase, but so also holds for the dot product. So distributive property. If we had vector A dot vector B plus vector C, this is going to yield the same result as vector A dot vector B plus vector A dot vector C. Okay, as you can see here. Okay, now the associative property with a scalar k. So if we had some scalar k multiplied by vector A, and then we did dot vector B, this is the same thing as moving this scalar to vector B. So A dot k times vector B, same thing. Another way you can rewrite it is k times A dot B. Okay, so it's associative. Doesn't matter what order you multiply these in, it's still going to yield the same result. Okay, so if the vectors vector A plus 3 vector B and 4 vector A minus vector B are perpendicular. Okay, what does perpendicular mean? I'm thinking dot product equals 0. Right? Perpendicular because, and we're going to come back to this because cos 90 equals 0. Okay, it also says the magnitude of vector A is 2 times the magnitude of vector B. It says determine the angle to the nearest degree between the two non-zero vectors A and B. Okay, so what we're going to do is we're going to find the dot product. Okay, so we have vector A plus 3 vector B dot 4 vector A minus vector B, and this is going to equal 0 because they're perpendicular. So let's go ahead and distribute. Vector A times 4 vector A, this is going to be vector A dot, 4 dot vector A dot 4 vector A dot vector A. I'm going to write the 4 in front, kind of like a coefficient, okay? And then vector A dot negative vector B. So this is going to be plus, but it's really going to be minus because it's going to be vector A dot vector B. And this constant being a negative, -1, is going to be pulled to the front, like the coefficient. Okay, keep going. Plus 3 vector B times 4 vector A is going to be 12 vector A times vector B. And then this last one, 3 vector B times negative vector B, or dot. Oh, I'm going to put a dot product there. I'm going to get -3 vector B dot vector B. And this is going to equal 0. Now let's simplify. So 4 times, so vector A dot vector A, we know from before, is going to be the magnitude of vector A squared. Okay, now these two here are like terms. So we have negative vector A dot vector B and then plus 12 vector A dot vector B. So we're going to have plus 11 A dot B. Okay, and then the last one, we have this -3 times the magnitude of vector B, and then this all equals 0. And now let's go ahead and substitute in 2 of the magnitude of vector B for every magnitude of vector A. So we're going to put all of this in terms of B. So this is going to be 4 times 2 times the magnitude of vector B. Okay, plus, I'm going to do this middle term in 2 steps. So first, I'm going to substitute in 11. So to see this vector A dot vector B, I'm going to go ahead and sub in the definition of the dot product, which is magnitude of vector A times the magnitude of vector B cos theta. Okay, then I'm going to bring this down, -3 magnitude of vector B. We can leave it like that because we want everything in terms of B. So in the next line, I'm just going to simplify the 4 times 2. So we get 8 times the magnitude of vector B plus, okay, this is where we change it. Okay, 11 times. See this magnitude of vector A? Again, we're going to sub in 2 times the magnitude of vector B. Then we have the magnitude of vector B, cos theta, minus 3 magnitude of vector b equals 0. Okay, I missed this squared on here. Okay. All right, and then the magnitude of vector a squared is going to be 2 times the magnitude of vector b squared. So this is actually 16. Okay, so now we're just going to collect everything. So we have 16 magnitude of vector b squared plus, well, what's 11 times 2? 22. Then we have magnitude of vector b times the magnitude of vector b, which is the magnitude of vector b squared, okay, cos theta, minus 3 times the magnitude of vector b squared equals 0. Okay, so if we think about it, we can add these two together, 16, that's going to be 13. So we're going to have 22 magnitude of vector b squared cos theta plus 13 magnitude of vector b squared equals 0. So all I'm going to do is bring over this term over here. Okay, so we have 22 magnitude of vector b squared cos theta equals negative 13 magnitude of vector b squared. Okay, and I'm going to just divide out. So I'm going to divide both sides by 22 magnitude of vector b squared. So 22 magnitude of vector b squared. And these are going to cancel out. The magnitude of vector b squared are going to cancel out. And we're going to be left with cos theta equals negative 13 over 22. Okay, we can put the restriction on here that the magnitude of vector b squared cannot equal 0 because that is a variable in the denominator. Okay, and then simply in order to get the cos off of the theta, we're going to cos inverse both sides. Okay, so we get theta equals 126.2 degrees. Okay, so the angle between these two vectors is 126 degrees. Okay, it's often necessary to square the magnitude of a vector expression. Okay, so here is an example. So example 4, if the magnitude of vector x plus vector y equals the magnitude of vector x minus vector y, prove that the non-zero vectors x and y are perpendicular. Okay, so we know that what we do to the left-hand side, we do to the right-hand side. And then that keeps our algebra balanced. So this is an example where we want to square the magnitude. So let's go ahead and square both sides. Okay, so in other words, what we're going to be doing is vector x plus vector y dot vector x plus vector y, right? Because that's squared. And now vector x minus vector y times vector x minus vector y, because again, squared. So let's go ahead and distribute or FOIL. Okay, so now we're going to have, and I'm going to do this the long way here. So we have vector x times vector x plus vector x times vector y plus y times x, so vector x times vector y again, plus vector y times vector y. Okay, and that's going to equal, then let's expand this, vector x times vector x plus vector x, no, that's going to be a minus because this is negative y. So vector x times vector y, okay, this middle term as well, minus vector x times vector y, okay, plus vector y times vector y. Okay, full expansion there. So from one of our first theorems, if we have vector x times vector x, we're actually going to have the magnitude of vector x squared. Okay, these two terms in the middle are going to add to plus 2 vector x vector y. And then vector y plus vector y is going to be vector y, like the magnitude of vector y squared. Okay, equals, same thing is going to happen with this vector x, magnitude of vector x squared. These two terms in the middle, we're going to have minus 2 vector x vector y. And then we're going to have the magnitude of vector y squared. Okay, so whatever is balanced, what we can do is we can cancel them out. So we have magnitude of vector x squared on each side. Those can cancel. Okay, so two ways to think of that. If you have like a scale and they're balanced, you can cancel them on both sides because it's going to equal the same thing. Okay, the other thing is that if you took this magnitude of vector x squared and you brought it over to the left-hand side, we would essentially get negative magnitude of vector x squared. So it would be like this minus itself. Okay, so ultimately it's balanced. Now, magnitude of vector y squared, those are also balanced. So what do we have left over? We have 2 vector x vector y equals negative 2 vector x vector y. Okay, let's go ahead and bring this over. So that gives us 2 vector x vector y plus 2 vector x vector y. And we can equate that to 0 because nothing is left on the right-hand side. So when we add these, we get 4 vector x vector y equals 0. Okay. Cancel out the 4's, divide both sides by 4. And now we have vector x dot vector y equals 0. Okay, so therefore, because the dot product here, vector x dot vector y, therefore vector x and vector y are perpendicular.